Hi folks, I'm sitting beside the Atlantic Ocean at Burnt Cape Ecological Reserve on the northwest tip of the island of Newfoundland, watching the ocean and a distant iceberg. My location may lead some of you to think this is a story about Newfoundland and Labrador. Although there is a distant link to the geology of Burnt Cape in Newfoundland and Labrador, the story today is about the rock that is very similar to the rocks that lie beneath the waves of an ancient ocean, similar to the ocean I'm looking at now. This is a story about a piece of ancient ocean floor and a rock called basalt that formed more than 2,700 million years ago. You can see and walk on that ancient ocean floor along the Southern Headland Trail at Pukaskwa National Park. In addition to the ocean floor chapter, I speculate about the relationship between the history of that ancient piece of ocean floor and an Arctic disjunct plant named Saxifraga paniculata, known informally as encrusted saxifrage. Join me as we walk along the Southern Headland Trail in Pukaskwa National Park on the north shore of Lake Superior in Ontario, Canada. Here we see a piece of ancient ocean floor and speculate how that ocean floor may have influenced the location of an Arctic disjunct plant species called encrusted saxifrage or Saxifraga paniculata. Pukaskwa National Park is located along the north shore of Lake Superior in Ontario, Canada. Within the park, there are several trails. The Southern Headland Trail is about 2 kilometers long. The trailhead starts at the Park Visitor Center and winds along the rugged coast of Lake Superior. In addition to the scenic views of Lake Superior, you get to see Haiti Cove, Pulpwood Harbor, and Horseshoe Bay. It takes a little over an hour to walk the trail at a leisurely pace, unless you stop to marvel at the cool geology and the Arctic disjunct plants that occur along the trail. In that case, the Southern Headland Trail can take a lot longer to hike. Recall that several Arctic disjunct plants occur in Pukaskwa National Park. These Pukaskwa Arctic disjunct plants occur thousands of kilometers south of their expected range in Canada's Arctic. Proximity to Lake Superior is perhaps the most important factor that contribute to the presence of these Arctic disjunct plants, which survive in this area long after the last ice age ended. It is the large, cold body of Lake Superior water that helps to create an Arctic-like climate in this coastal region. Okay, let's put on our scuba gear and explore the Earth's oceans. About 71% of the Earth's surface is covered by water. The oceans hold about 96 to 97% of all the Earth's water. That's a lot of water. Have you ever wondered what lies beneath the ocean waves? This historic map of the ocean floor beneath the Atlantic Ocean shows that the ocean floor is not a flat, featureless landscape. It's full of valleys, canyons, mountains, and plains. This map is the result of the pioneering work by people like Marie Tharp, who studied the topography of the ocean floor. Although it looks like we know a lot about the ocean floor, let's not forget that as of about 2017, only about 6%, that's 6% of the ocean's floor had been mapped in detail. Have you ever wondered what the ocean floor is made of? Well, the answer is basalt. Today and in the past, ocean floor basalt forms at ridges that occur along the middle of the Earth's oceans. These are called mid-ocean ridges. At the ridges, the rocky surface of the Earth, called the oceanic crust, is torn apart by geological forces to create a ridge and a valley on the ocean floor. In Iceland, you can actually see the mid-Atlantic ridge and the valley or rift zone, where the oceanic crust is being torn apart. This is one of the very rare places where you can see a mid-ocean ridge exposed on the land surface. Along the mid-ocean ridges, liquid rock called magma wells up from deep within the earth to fill those rifts. As the magma cools, it becomes ocean floor, and almost all the ocean floor is made of basalt. Now, I'm not talking about any basalt. I'm talking about pillow basalt. When basalt magma erupts and cools underwater, it forms features called pillows, and the rock is called pillow basalt. The presence of pillow features is part of the evidence that tells a geologist that the basalt formed underwater, likely as ocean floor. Of course, the story of pillow basalt is much more complex, but this understanding is a good place to start. When basalt magma cools in a way that it is isolated from cold ocean water, individual mineral crystals form, and the magma does not form pillow features. Geologists call this massive basalt or gabbro. Again, this is a very simple understanding, but it is a place to start to understand what we will see along parts of the Southern Headland Trail. So, what do pillow basalt and ocean floor have to do with Pukaskwa National Park? Well, let's take a look at the rock exposed along the Southern Headland Trail. As we walk along the trail from Horseshoe Bay Beach to the Southern Headland, we see two types of basalt and evidence of powerful geological forces that transform the rock. The first rocks we see are round outcrops of basalt. We see two features that tell us we are walking on smooth surface that geologists call massive basalt or gabbro. First, we don't see any pillow features on the smooth rock surface. Second, if you find an area of rock that is lichen-free, you can see green mineral crystals that are 1 to 3 millimeters in length, sitting in a light-colored background or matrix. These green minerals grew large because the magma cooled slowly. That means the magma was not in direct contact with seawater. So the absence of pillows and the presence of visible mineral crystals confirm this as massive basalt or gabbro. Now both gabbro and basalt are types of igneous rocks, that is, both cooled from the same type of magma. However, basalt erupted onto and flowed over the surface of the ocean floor. On the other hand, gabbro cooled slowly within the earth, so mineral crystals had the opportunity to grow large. But, as illustrated in this cartoon, the center of thick basalt flows can contain larger mineral crystals and look like gabbro. So, sometimes it's tricky to distinguish gabbro from basalt. Geology requires some detective work. As we walk farther along to the north edge of the Southern Headland, we come across basalt with these beautiful elliptical features that look a little bit like bread buns packed together. Geologists call these pillow features. They are diagnostic of basalt that erupted underwater on an ancient ocean floor. Look closely at the outer rim of an individual pillow. The outer edge is commonly recessed because it is soft and erodes more easily compared to the pillow core. Also, the edge is darker in color compared to the pillow core. Geologists call this rim a selvage. The selvage represents liquid basalt that cooled and solidified really quickly against the cold seawater. The selvage contrasts with the core of the pillow, which cooled more slowly and retained liquid for a longer time after the basalt erupted onto the ocean floor. Many pillows are tube-shaped, and basalt liquid actually flows through the tube to feed and make other pillow tubes. This photo from Gros Morne National Park in Newfoundland and Labrador shows a tilted surface of an actual piece of ocean floor. The elongate worm-like features are the pillow or lava tubes. Why don't we see the worm-like shapes of pillow lava tubes here on the Southern Headland? Well, to see the tube shape, we would have to look down onto the top surface of the pillow tube. Normally, that means looking down on a flat horizontal surface, like looking straight down at a straw lying on a table. We see a few pillow shapes that look sort of like tubes, but unfortunately, most of the time on the Southern Headland Trail, we are walking over and looking down at a cross-section cut through the pillow tube. It is as though we were looking down on the long axis of a vertical straw, so we see a circular or elliptical shape. That is the illusion of geometry. It's safe to assume that the pillow basalt on the Southern Headland Trail erupted onto a relatively flat-lying ocean floor, but thanks to the powerful geological forces, that horizontal ocean floor was tilted into a vertical orientation. Hence, we don't see pillow tubes, rather we mostly see pillows with an elliptical shape. The power of geological forces. Now that we have established we are hiking along the Southern Headland Trail on what was once an ocean floor, you might wonder, how old is this former ocean floor? Geologists use different tools and other geological observations to determine the age of a rock. Yes, you can date rocks. I know, you thought geologists were weird. Now you are convinced that anyone who dates a rock is weird. These pillowed and massive basalts are older than 2,700 million years old. These are really old rocks. So, preserved here in Pukaskwa National Park, where you are standing, is an ancient piece of ocean floor that formed early in the Earth's history, at least 2,700 million years ago. How cool is that? Another history chapter of the basalt rock unfolds as you walk from north to south across the Southern Headland towards Lake Superior. Long after the basalt erupted onto the ocean floor, the rock was buried deeply in the earth, where powerful geological forces completely transformed the basalt to the point where it is barely recognizable on the headland. If you look carefully, you may see a feature that records that rock transformation. The feature consists of zones of rock that exist now as thin layers, sort of like pages in a vertically standing book. The zones are not easy to see because the lichen conceals that part of the rock story. Those thin rock layers formed when the basalt was heated, became weak, was squeezed, and was stressed while buried deeply in the earth. Geologists call this sheared rock. Yes, even rocks get stressed out. It's noteworthy that there appear to be many individual plants of encrusted saxifrage in this area of sheared basalt. I wonder why that is. Tufted bulrush, shrubby cinquefoil, and two Arctic disjunct plant species, namely Mistassini primrose and common butterwort, also grow in this moist area on sheared basalt. Like encrusted saxifrage, common butterwort and Mistassini primrose are calcicolous plants, which thrive in calcareous or calcite-rich habitats. Something that may account for the apparent abundance of calcicolous plant species in this area is white calcite precipitate that occurs on some surfaces of sheared basalt. The white precipitate indicates the burial, heating, and shearing of the basalt rendered calcium in the rock available to react with local groundwater and the atmosphere to precipitate the mineral calcite. The calcite precipitate indicates this area of sheared basalt and the local water seeps have a calcareous chemistry. So the abundance of encrusted saxifrage and other calcicolous plant species in this area is consistent with the calcareous habitat related in space to the sheared basalt. Well, let's draw this video to a close. I emphasize that plant abundance is based on my subjective impression, and subjective impressions do not constitute scientific proof. So we should all be cautious about my suggestion that encrusted saxifrage and other calcicolous plants are abundant in this area of sheared basalt. I also made lots of assumptions, and recall, I'm not a botanist. So perhaps you can test these ideas if you're fortunate enough to hike this part of the Southern Headland Trail. So to answer the question about a relationship between geology and plants, let's summarize what we saw. We walked over massive and pillowed basalt. The basalt is a preserved piece of ancient ocean floor that formed more than 2,700 million years ago. The ocean floor basalt was subject to great geological forces, during which it was buried, cooked, sheared, and tilted to vertical well deep within the earth. Once exposed on the Earth's surface millions of years after the basalt was cooked and sheared, groundwater and surface water extracted calcium from the rock, which locally precipitated white calcite. That created a calcareous habitat in the area of sheared ocean floor. The calcareous habitat supports abundant encrusted saxifrage and other calcicolous plant species that remain in this area nearly 10,000 years or longer after the ice sheets melted away at the end of the last ice age. So, might there be a geological influence on the location of these plant species? I suggest yes, there is. So, if you get a chance to hike the Southern Headland Trail at Pukaskwa National Park, pause for a moment and reflect on the amazing geological history that lies beneath your feet, and marvel at the synergy created by the local geology, its history, and some specialized calcicolous plant species, including at least one Arctic disjunct plant named encrusted saxifrage, Saxifraga paniculata. And that is one part of the geological world along the Southern Headland Trail in Pukaskwa National Park, as seen through the eyes of a geologist. Thanks for watching.